So the story of motors okay, I don't know why this happened. Yes. So the story of motor that you applied current I. So this current I generated a force. This force moved the wire with a velocity v. When the wire moves and cuts the flux, it will generate an EMF, and this EMF is opposing I. And this is how the motor is reacting. So the motor is reacting, is moving just to generate this E against the injected current I. The relation between I and force is the force equal to B I L sine theta. The relation between force and velocity V, this is a mechanical equation, okay, which is F acting equal mass acceleration. So this is the mechanical system. Once you have a velocity v or the wire start to move, it will generate E, and the relation between E and V is velocity, okay, that E equal to BLV. And these are the equations that governs the operation of motors, which later on will be translated into set of equation, equivalent circuit, and even block diagram for control. Okay, just this story. The story for generators. So let's go back to the generator action and complete it. So for the generator action, we said that if you move with an F input, which is a mechanical force input, you moved the wire, so the wire cuts the flux, and once the wire cuts the flux, it will generate a voltage E. Now if you closed the circuit with a resistance R, which is the load on the generator, so this E will circulate current I. So there is I going from this E, because E is the source here in the circuit. Now you will have the motor action too, because you have I, you have phi, and you have a wire. So we need to use the left hand rule. So we need to use the left hand rule. So the current is going in this direction. So the current is going in this direction, I, flux into your hand. This will be the direction of the force. So here we will have an induced force in this direction. So this is an F induced from current. And you can see that the induced force is against the input force. So for the generator, you start to move the generator mechanically. So the reaction of the generator should be mechanical against your movement. And for the generator to generate this mechanical force, there should be a current circulating to generate this mechanical force. So to generate this mechanical force, the generator needs to circulate current, which is producing electricity. So the electricity produced in generator actually is the byproduct to generate this opposing force to the acting force. So if we write down the story for generators, so you have F input, which is a mechanical force input. This input force will move the shaft, or will move the wire, or will move the motor with a velocity v according to the mechanical system equation. And this velocity v will generate a voltage E according to the equation BLV sine theta. Okay, just we can assume that theta is maximum, as we will see for DC motors. And this E will circulate current I according to circuit analysis. Okay, so So this is my equation, okay? This is not my equation. So E will circulate current I according to circuit analysis. We can find the relation between E and I. This I will produce force F induced according to the equation BIL sine theta, and this induced force is against or opposes the input force. And this is the story for generators. So when you acted by inputting a force, the generator is trying to react with a mechanical force. To be able to get this mechanical force, the generator has to generate current I, and to generate current I, it has to produce E. So the electricity you are getting is actually a byproduct from generators. Now, when you load the generator means you turn on more light. When you turn on more light, you take more current. And if you take more current, you are producing F induced more. So you will feel this, that the shaft of the motor or of the shaft of the generator is getting heavier. It's harder to move the shaft as you take more electrical load. So when you throw more electrical load on the generator shaft is slowing down because you are taking much more energy, or you are producing more mechanical energy. So this mechanical energy, F induced, is actually a dragging force, or a force that opposes the movement. This is how the generator will react to loading. And this is the story for motors and the story for generators on basic terms, okay? So the second part is the construction and theory of operation of DC motors. So let's start by identifying what are the needed components in construction, and while we are explaining the construction, we will go through the theory of operation. So assume that we have a coil, okay? So assume we have a coil, and the coil means we have two conductors like this. So this is like one turn coil. So this is one turn coil. And the first challenge that we will see here is how we can inject current into this coil, or how we will collect the current from the coil if it is motor or generator. So how we can inject the current if it is motor, or how we will collect the current if it is generator. Why this is a challenge? Because the coil is rotating, it's moving. And if it is moving and you have wires here, and this coil is rotating, the wires will get tangled and it will be broken. So the first challenge that we will see in motors or generators is how we can collect the current while it is moving. And let's take a practical example to understand this part here. So if you look at the LRT, so we are missing E5 and E7. So if we look at the LRT here, you will see a similar issue. So these wires are the supply, and you need to feed current from this supply into the electric vehicle or into the car. So we need to supply current here. So if we have a solid cable, here connected, while this one is moving, while this car is moving, it will be an issue. It will break. So how they solve this? They solve this using the idea of sliding So what we have here, we have what is called a brush, and this brush is sliding on the wire, and this is the wire, and you have here a spring to keep firm connection between the wire and the brush. So this brush here is conducting material which is connected to the cable going inside the car to supply the car, and this brush from conducting material, the spring is pushing this brush against the wire to keep good contact, so you have a good contact with the wire while this car is moving. And this brush is made from a soft material, so with time the wear and tear will happen to the brush. So all the wear and tear will happen to the brush, not the wire. So you can change the brush regularly during maintenance. And this is the idea of sliding, or we call it slip rings. So this is the idea for what is called a slip ring. So we use a slip ring to be able to connect current to a moving coil. So to be able to connect the current to a moving coil, we can use this idea of slipping, or this idea of sliding over the coil. So what they will do, so here is the wire here. They will have two rings. So this is the first ring and this is the second ring, and they will connect the first wire to the ring, the second wire to the ring. Then they will touch these rings using brushes. So as we mentioned, these brushes will be pushed against the ring to keep good contact. And here we will have the wires so these rings will be rotating with the coil. So when these rings are rotating with the coil, we can have a solid connection here because there is no relative speed between the ring and the coil. And this brush is touching the ring, and this brush is connected to the wire. So this wire actually is connected to this part, and the other wire here is connected to this part through the brush. So this is the first issue. So we use slip ring and brushes, and this is a big issue for this kind of machines. And this is where Tesla did his breakthrough. So Tesla is the first engineer ever who invented a way to get rid of brushes, and he invented the brushless motor. So these brushes are the main disadvantage of these kind of motors, because these brushes need to be maintained. You need to change the brushes regularly. So let's see how this works. So I will move this page up here. Okay, now let's see what will happen as a voltage. So what we will do, we will take a coil, and this coil is subjected to flux. So here we have a magnet, and this magnet is generating flux. And here we have, these are the rings. And here we have our brush, and this coil has two sides. This coil has a side A Okay, let's see what is going on here. So this coil has side A, side B, side C, side D. And at this position, the angle between the coil, so don't forget that the voltage generated E equal to BLV sine theta, and the theta is the angle between the coil plane and flux. And the coil plane angle is a perpendicular vector to the plane. So here the coil is horizontal, so its vector is going up, the direction for the coil. So the angle between the coil direction and the flux is 0, which will give us a voltage 0. So when this coil is horizontal, we are generating a 0 voltage, so E equals 0. Now we are assuming that the coil will rotate, so here is A, B, C, D. So we are assuming that the coil is rotating in this direction. So the coil rotated 90 degree. So here is the direction of the coil, which is perpendicular to the plane of the coil, and the direction of the flux is going up. So this angle is 90 degree. So in this case, E equal to BLV, or equal to E max. So in this case, the voltage will be max. And as you can see that the voltage changed from 0 to max as a sine wave. And it is a sine wave because E equal to BLV sine theta, and theta is omega t. So with the time going on, your voltage will be a sine wave. Then the coil will go to horizontal position again. So here is A, B, C, D. So we are assuming it is rotating clockwise. So in this case, the direction of the coil, this is the coil direction, and here is the flux direction. So the angle between the coil and the flux is 0. So E equals 0. So we are going back to 0. And then the coil will go down. So here is A, here is B, here is C and D. In this case, the direction between the coil and the flux is 90 degree. And if you apply the right hand rule, you can see that the voltage is negative. So the voltage here is negative E max. So the angle, you take the angle from the flux and you go to the plane direction. And in this case, the voltage will be negative E max, or E max negative. And finally, if the coil goes back to the horizontal position, the voltage will go back to 0. And now we did a complete cycle. So if we take one coil This is one coil, and we need to sketch the voltage between these 2 points. Here is A and B, and we need to find E in this coil. We can see that this EMF versus time will be a sine wave, and we can prove this by taking this coil into various positions. So we will take this coil first horizontal, so here is A, B, and we are assuming that the flux is going, say, down. So, and we are rotating in this direction, so the direction of the speed is going up. So if you receive the flux into your hand and your thumb is pointing to the direction of the rotation, you can find the direction of the EMF using the right hand rule. So you can find that E will be in this position, and this E is 0 because the angle is 0. Then if you take this coil to be vertical, in vertical position, here is A, B, C, and D. This is the direction of the coil, and the flux is still going down. So your voltage will be in this direction E, and it will be maximum. Now if the coil goes back to the horizontal position again, in this case the flux is still going down, and the direction of the flux will be making 90 degree, and in this case E will be 0. So here E equals 0, here E equal max, here E equals 0. Then the coil will reverse. Here is A, B, C, and D, and the coil is moving in this direction. This is the direction of the flux. Now if you put or if you calculate the direction using the right hand rule, so let's bring the right hand so you can see it. So we will be receiving the flux into our hand, and here is the direction of movement, and we are receiving the flux into our hand. So this will be the direction of the voltage. So here will be negative and here will be positive E. If you look at the direction of this E here and this E here, you can see in this case A is positive, and in this case A is negative, which means that in this case E is negative E max. And this will be the sine wave that we sketched here for the voltage, which will leave us with a question. And the question is the EMF is AC, how the chapter is about DC machines. And this is a question.